The perimeter of Denver International Airport spans over 50 square miles. At night, securing a boundary of that magnitude becomes a staggering logistical challenge. During a routine night departure to Los Angeles, a Frontier Airlines Airbus A320 began its takeoff roll, accelerating rapidly down the runway into the high-speed regime. This diagram illustrates the aircraft's acceleration. The A320 requires roughly 135 knots to achieve liftoff. As the aircraft reached 127 knots, fractions of a second before rotation, it struck an unauthorized pedestrian who had walked onto the active runway. The individual was ingested into the running engine, causing immediate internal damage and fire. The cabin rapidly filled with smoke drawn through the air conditioning packs, forcing the flight crew to deploy the spoilers and execute an emergency high-speed rejected takeoff. The A320 is equipped with expansive flight deck windows and high-powered taxi and landing lights that illuminate the tarmac. Yet, the flight crew had zero visual warning that a person was in their path. A pilot's visibility during a high-speed takeoff roll is not absolute. It is severely restricted by a combination of airframe geometry, kinematic tunnel vision, and intentional systemic design. To understand how a pedestrian goes unnoticed on a lit runway, we have to look closely at the physical architecture of the aircraft itself. This wireframe shows the scale of the A320. The flight deck sits approximately 30 feet above the tarmac. That elevation immediately creates a vertical disconnect between the crew and the ground environment. From that elevated seating position, the physical pitch of the nose blockades the lower visual field. Inside the cockpit, the glare shield, the panel housing the primary instruments, pushes that downward viewing angle even higher, severing the sightline to the immediate foreground. This creates a permanent structural blind spot directly beneath and ahead of the aircraft, extending outward for 30 to 40 feet. For perspective, that is a blind zone long enough to completely hide two standard passenger cars parked nose to tail. Any object standing within 40 feet of the aircraft's nose is physically erased from the crew's visual field, regardless of how brightly the runway is illuminated. The airframe provides the static geometry, but the physics of acceleration compound the problem further. As an aircraft accelerates, approaching 100 knots, the human eye struggles to process near-field objects. Immediate surroundings degrade into violent motion blur, risking spatial disorientation. To counter this, the pilot flying must rely on a specific optical technique to keep the aircraft perfectly aligned with the runway centerline during acceleration. This diagram illustrates what pilots call infinity focus. Instead of tracking the ground directly ahead, the pilot anchors their vision on the furthest visible runway lights at the horizon. By locking onto that distant point, the brain actively suppresses peripheral and near-field visual data. It is a necessary biological filter to maintain directional control at high velocities. The faster an aircraft moves, the further away the pilot's functional reality begins. The immediate 100 feet of the runway ahead effectively ceases to exist in their conscious perception. Physiology is heavily managed by the systemic procedures of cockpit resource management. A commercial takeoff roll requires absolute precision, demanding a strict, non-overlapping division of labor between the two pilots on the flight deck. As shown in this breakdown, the pilot flying has exactly one external visual responsibility: driving the aircraft down the runway centerline. The pilot monitoring maintains their focus entirely inside the cockpit. Their duty is to constantly scan engine parameters, track V-speeds, and verify the mechanical health of the acceleration. Neither of these highly specialized roles involves looking out the side windows or scanning the dark runway perimeter for foreign objects. Human attention in a modern flight deck is heavily regimented. Pilots are systemically prevented from casual observation of their surroundings to ensure absolute precision on tasks required for aerodynamic survival. That focus tightens even further once the aircraft hits a critical technological threshold: 100 knots. Crossing 100 knots places the aircraft into the high-speed regime. At this momentum, aborting a takeoff violently stresses the brakes and tires, introducing massive risk to the airframe and passengers. This interface is the ECAM, the Electronic Centralized Aircraft Monitor. It serves as the primary diagnostic tool during this dangerous phase of flight. To prevent a panicked high-speed abort over a minor issue, the flight computer activates inhibit logic.
It deliberately hides non-lethal system warnings from the crew, ensuring they only see information that strictly threatens the immediate safety of the flight. In this regime, pilots are trained to reject a takeoff for only 5 catastrophic events: engine failure, engine fire, engine damage, flight control failure, or a red ECAM warning. Notably absent from the ECAM's programming is any form of biological obstacle detection or perimeter ground radar. Once the aircraft surpasses 100 knots, both the human crew and the onboard computers actively filter out environmental noise. They strip away situational awareness to focus entirely on successfully lifting the aircraft off the ground. Returning to the Denver incident, we can now map these variables onto the final moments before the impact at 127 knots. First, the nose's physical architecture blocked downward visibility, placing the pedestrian in a geometric blind spot. Second, the pilot flying's vision was anchored far down the runway, bypassing the near-field environment. Finally, the pilot monitoring was internally focused, and the ECAM possessed no perimeter sensors. The failure to spot the pedestrian was not a lapse in pilot observation. It was the manifestation of an aviation system operating flawlessly as designed. High-speed commercial aviation relies entirely on a single foundational assumption: the absolute sanctity of the sterile airport perimeter. When that perimeter is breached, as documented in Milan, Daytona, and now Denver, the system has no fallbacks in place. Until takeoff systems are redesigned to include forward-facing ground detection, anytime an unauthorized individual enters the high-speed environment, the flight deck remains physically, visually, and technologically blind to their presence until the exact moment of impact.